Okay, so last time I was talking about these complex organic molecules arriving on Earth from comets. The presumption is that perhaps life originated elsewhere in the solar system and just perchance got to the Earth through either comets or meteorites. All right, so let's continue. So here's a meteorite that fell in Australia, containing different amino acids that are used. Amino acids, of course, again, are the building blocks of proteins. There's actually lots and lots of amino acids. There's I think there's like more than 500 of them, but there's only like 20 or so that are used for living organisms on Earth. All right, so what about cosmic evolution? So you have these simple one-celled creatures like algae that appear on Earth at least 3.5 billion years ago. And then we see the arrival about 2 billion years ago of more complex creatures, still one-cellular. Then about 1 billion years ago you get multicellular. And then, of course, evolution takes off after that in much more complex ways. And in fact, the human civilization, and the reason that they're bringing this up, well, the human civilization, as far as our recorded history, this actually goes back before recorded history, is roughly 10,000 years. That's basically when humans started to become farmers around the world. Not every civilization was completely agrarian, but many had at that point in time, and that's generally when civilization is considered to have started. But the reason that that's important is you think of this 3.5 billion years of life on Earth, and only the last 10,000 years, which is just nothing. That's a very short amount of time, where human civilization gets complicated, or gets sophisticated enough so that we can build the kind of technology to detect life around other star systems, or even try to communicate with other star systems. Or anyhow, here's a little side note about viruses. So remember, one of our questions was, what is life? And so the problem with viruses is they don't live on their own. They actually need a host, and then they become what would be considered living. So like a virus by itself is not. I don't know if it's really alive or not, and so we're not really sure, and that's considered what's called a gray area. And so there might be other chemical situations, if you will, of something that might be alive, if certain conditions are right. If it has a host cell or some kind of host to continue its existence. All right. So life on our planet is completely carbon based. All the molecules of organic molecules, if you will, are always they always have carbon in them, and there's a good reason, good chemistry reason for that. Carbon likes to bond with lots and lots of different things, including itself, and of course we know that you need water. Water is this incredible substance that allows life to thrive on this planet. So and that's really been the focus of looking for life within the solar system, is to pretty much follow the water. That's been the standard concern, or the standard approach to looking for life within the solar system. You find liquid water, and that will eventually lead us to life. And we spent a lot of time looking for liquid water on Mars. We have found some. We think that some of the icy moons of the gas giants, like for example Europa, the moon of Jupiter, has a ice surface, but we think there's a liquid ocean under it. And then, of course, Enceladus has a liquid ocean underneath its icy surface, and we've even seen geysers, saltwater geysers, erupting from the south pole of Enceladus. And of course, there is also the possibility of microbial life in the clouds of Venus. There's some evidence where that's a possibility, and that needs to be investigated further. All right, so of course this is what we spent a lot of time doing this, sending rovers to Mars. Thus far, there's been Spirit and Opportunity, and also Curiosity. There's actually another one that should be there soon. I think it's supposed to get there in February of 2021. Called what is that called? Perseverance, and it even has like a little helicopter that's going to go flying around Mars. So hopefully that particular spacecraft will get there and deploy properly, and we'll get to see a lot more of Mars than these. The rovers have been very, very slow. They travel really slowly, and so they have gone miles and miles when you consider it, but it takes years and years for that to happen. With a helicopter, you're going to be able to move a lot faster across the surface of the planet. Well, not across the whole surface. But. All right, so and one of the things that we found is life can exist in different parts of the planet that we never even thought that to even look for life in these different places, because we thought they were just inhospitable to life. But there are things called extremophiles, where these living things exist and thrive actually. Some of them are in these thermal vents at the bottom of some of the oceans, where there's no sunlight at all. There's even situations in the Arctic where there's living creatures in the ice. Not creatures like not animals. But these are usually plants or plant-like life. Like algae and things like that. All right. Let's see. So some people have thought, well, carbon, that's wonderful. Carbon is a wonderful molecule here on Earth. But what about silicon? So if you look in the periodic table, silicon it has the same chemical, very well similar. Let me put it that way. It's not exactly the same, but very similar chemistry to carbon. Now, silicon does have some differences, of course, but some people have proposed, perhaps silicon could, instead of having liquid water, you could have liquid ammonia or liquid methane, and maybe a silicon-based life could thrive in something like that. But we don't know. There's some evidence that it could be too cold or so forth. Back in the 1960s, I think it was, there was this guy, Drake. He was an astronomer, and he came up with this thing called the Drake equation, which has been looked at for a long time. But really, the thing that's changed as far as the Drake equation goes, it's this thing that, what fraction of the planets out there have life on them, and what fraction of the life turns into intelligent life, and so forth. How many planets exist in the habitable zone where liquid water can exist, and things like that. So, when Drake originally wrote this equation, we had no idea how many planets were out there. And in fact, now, in the 21st century, the beginning part of the 21st century, we're still finding out that there's lots and lots of planets, and there's planets in places that we had no idea. That Jupiter-sized worlds really close to the sun, and of course they probably have moons. And we haven't detected those particular moons yet, but perhaps living things can exist. A lot closer to the sun, a lot closer to their stars, not our sun, of course. Their stars, and it just kind of expands this our ability the possibility of life in different locations around our galaxy. So this is this is all of his equation. I used to be really fascinated with this equation and so forth. It's not as interesting anymore because I think it kind of needs to be rethought as far as there's many different ways. Like, you have to make some assumptions about some of these things, and one of the results is that there's when you do this calculation and you make all these assumptions, is that the number of technological intelligent civilizations that arise in our galaxy might just be one. It's just us. But we don't know. The answer is ultimately we really don't know. So I'll just kind of go through this. This has to do with the number of new stars that are forming in our galaxy, roughly 10 per year on average. The fraction of planet F. This thing we're really figuring out now. When Drake wrote this famous equation, nobody knew how many stars had planets around them. And now it seems that most stars have planets. And we're finding, multi-planet, stars that have many different planets around them. Again, we really don't know. We don't know how many of these types. This is about stars. I'm going to skip this. Because you could have, even really low temperature stars could have habitable zones that are really close to that particular star. So, I know this is an Astronomy 101, which we're just interested in. We're not really talking about stars so much, but anyhow, let's move on from that. We really think that really close to the center of our galaxy would not be really good for living things because of the intense radiation. So there might even be a galactic habitable zone. But again, maybe there are situations where life can arise and utilize that radiation. We really don't know. Let's see. There are over half the stars in our galaxy are actually in binary systems. That is, two stars orbiting each other. And there's some question as to whether intelligent life can arise from a planet that's orbiting two different stars. Again, we don't know. We really don't know. Especially if it's the thing about Earth is things have been very stable for billions and billions of years, and that stability has allowed life to flourish, to evolve, and if things were on a planetary scale were changing rapidly, life just would not